Justin Miller, our college physics here, and we are going to continue onward with some wave mechanics. So we're going to deal with, in this particular segment here, transverse waves that are constrained to a string. So waves on a string. We're going to look at transverse waves on a string. These are traveling waves, and we know that the displacement as a function of position and time can be written as a times the sine of k x put minus plus omega t plus phi. It's minus, then we've got the wave traveling to the right in the positive direction, positive x direction. If it's plus, it's traveling in the negative x direction. So that's good, we already know that. That's fantastic, that's for any wave in general that's sinusoidal. Now we're talking about waves on a string. Well, when it's constrained to a string and it's transverse, there's certain other aspects that are of general interest. So we think about this, right? We've got ourselves some wave here that's traveling. The wave is traveling this way with some wave speed v, right? Well, what's really happening? All these elements of the wave itself, all the elements of the string, I should say, are really just going up and down. They're like little simple harmonic oscillators themselves. And we already talked about that in the last lecture video. So what else could we discuss regarding, say, one of these points? Well, what's this point going to do? What's it going to do next? Well, you look behind it and see, and it's going to go down first, and it'll go down, and then what's it going to do next? It's going to go back up to the maximum amplitude. And it's going to keep doing that as time goes on, oscillating up and down. And this would be the case for any point along the string. All it does is go up and down and up and down. And it seems like the string's moving that way, but it's really just the waves that are moving to the right. Anyways, just say all points on the string merely move up and down like a simple harmonic oscillator, like a show. So what can we talk about? Well, we can talk about the individual motions of any element of the string as it moves up and down. Like, hey, what is its velocity moving up and down? What's its acceleration moving up and down? But instead of calling it just velocity and acceleration, we're going to call it transverse velocity and transverse acceleration, so we don't confuse it with the wave velocity itself, the wave energy traveling, not the wave energy, but the wave traveling to the right. So let us define. Transverse velocity as the velocity of an element of wave as it moves in its transverse direction. And I'll just put up and down, in our case, the way that we've got things situated there. Well, what do we do? Well, we'd have to be able to say, I want to know what the transverse velocity is of this point, or this point, or this point. Because within one cycle, every point has a different transverse velocity. It has a speed and a direction, up or down, and a particular rate that it's traveling at. And we note that at the end points, as it gets up to its maximum, that's when it's going to start going back down. So we'd have that the transverse velocities at these endpoints, at plus and minus a, if you will, have to be equal to 0. And as it transits through the equilibrium position, that's when it's going the fastest. Because again, it's just like a simple harmonic oscillator. But now we're talking about across any point on the wave itself. So how do we describe that? Well, the transverse velocity, which we're going to call v sub y, is equal to dy by dt at some x is equal to some constant value. So we pick an x, pick a position along the string, and say, hey, what's its transverse velocity? When? Well, at some specific moment in time. We'd have to know the time too, but we gotta pick a position. So x is gonna be constant. And what does this do? Well, this gives us the ability to write it like this. V sub y is equal to dy by dt. I don't know if you've seen this before, but these are partial derivatives, and partial derivatives just take the derivative of some function with respect to only the variable, explicit variable here. Here. D by dt. So if something's implicit, we don't worry about it. It's only the explicit variable that we worry about taking derivatives of. So actually, partial derivatives are much easier to deal with than full derivatives. Nonetheless, this is what we've got going on. V sub y is then equal to the partial derivative of, well, what is y? Y is going to be equal to a times the sine of kx. And let's just say it's traveling to the right. Kx minus omega t. We can still put in phi here. And what are we going to get out of this? Well, it doesn't matter about x. We just treat x like it's a constant value. So this little term here doesn't really even do anything. So we're taking the derivative of sine. What's the derivative of sine? That's right, the derivative of sine is cosine. But then we've got this negative omega t. Sine's an odd function. The negative sign can come out. And we've got ourselves that v sub y is then going to be equal to negative a, and then we've got this omega t that we're taking the derivative with respect to, negative a omega times the cosine of kx minus omega t plus phi. So there is the transverse velocity at some position x at some time t. Given that we know what the angular frequency is, we know what the wave number is, we know what the phase constant is, and we know the amplitude of the wave itself. Fantastic, fantastic. So what can we do with this? Well, we can again compute what the transverse velocity is. It could be positive, it could be negative. Going up, positive. Going down, negative, by convention. So what else can we do? We can also define transverse acceleration. Call that a sub y is going to be equal to, we're doing the same sort of thing here where we're keeping x constant. We're just looking at a standardized position, this position, or this position, or this position. We're not letting x vary or anything. So x is some constant that is being evaluated at. So that gives us the partial derivative of v sub y with respect to time. So it's still the time derivative of velocity, but now we're just taking the partial once again. And what do we get out of this? This is going to be equal to, well, we take the derivative of this right here. Cosine's an even function. We've got this negative sign there that doesn't end up doing anything. And we've got another factor of omega that comes out. And we got that omega t in there. That comes out. Cosine, derivative of cosine is a negative sign. Those negative signs cancel out. And then got a negative sign there. That negative, negative. Negative omega comes out from there. Yeah, that's what comes out. Anyways, this ends up being negative a omega squared sine of kx minus omega t plus phi. So we've got these two expressions. Let's just look at them really quick at a nice position for a particular phase constant, just to make sure that what we have here makes sense. So we're gonna let phi be equal to 0 and look at t equals 0 and x equals 0. So this is a picture of the function with phis equal to 0 at t equals 0 and x equals 0. A times the sine of kx minus omega t plus phi for the wave traveling to the right. Correct? Correct. So we're going to look at this point right here and say, well, what's this point going to be doing? Well, that point right there is going to be moving up or down. And what do we have to look at to be able to make that characterization? Look at what's coming next. We look at behind it. And what's behind it? Well, this is. So this point, as this comes in to be, this point's going to sink down. And then it's going to go back up. So we should have that the velocity, the transverse velocity, is negative because it's going down, right? And it should be a maximum value as well. So we have that phi sub y evaluated at x equals 0, t equals 0 is then equal to negative a omega times the sine of, well, sine of 0. Because x and t is equal to 0 and phi is equal to 0. What's the sine of 0? That's right, sine of 0 is equal to 1. And we just get that this is going to be equal to negative a omega. Negative says going down. And the greatest value that this can be, right here, oops, I boxed the wrong one. It's this one. The greatest value that the transverse velocity can be is a omega. What did I do there? Sine is 0, sine 0, cosine. My mistake. Cosine there, what am I doing? I wrote sine, I meant to write cosine. I've seen cosine, I'm saying sine. Anyways, cosine of 0 is equal to 1, sine of 0 is 0. And we've got ourselves this. Maximum value that it can be is a omega, and we've got that it's transiting through the equilibrium position, and we know for a simple harmonic oscillator that's when it has its maximum speed, as does the element of a string have its maximum speed. It's going down, check. Let us look at a sub y evaluated at x equals 0, t equals 0. A sub y is equal to negative a omega squared times sine of, well, now it's going to be sine of 0. Sine of 0 is not 1, it is 0. So this is going to be equal to 0. We have that at x equals 0, t equals 0, the acceleration is equal to 0. Well, as it's going through this equilibrium position, what do we have? There's no restoring force acting on it, just like a simple harmonic oscillator, right? That's where the acceleration is 0. It's when it's furthest away where the acceleration is a maximum. So there we go. We've got it. And we could look as time goes on and we'd find, yeah, the acceleration at this point as it continues to go down ends up being positive because it's going to be slowing down as it's going down. So the acceleration is the opposite direction. We've got this whole correlation with the acceleration, the velocity, and the position with respect to time as this wave travels through time. All right, so these are two nice expressions that again allow us to discuss a little bit more about transverse waves. And also got that if it's a wave on a string, which we're talking about right now, so for a wave on a string of linear mass density, mu, and tension, t, the wave speed is given by v is equal to the square root of t divided by mu. So there's the wave speed for a wave on a string. What does it depend on? It depends on the linear mass density of the string. It's mass per unit length. And it depends on the tension in the string. So this goes back to things that you can start thinking about with strings or stringed instruments, guitar, piano. take a guitar and you start winding up the tuning key so it gets tighter, and what happens? The pitch gets higher because the wave speed's changing for a given string with linear mass density mu. Let me grab something really quick, see if I can kind of show this without too much trouble. Try not to knock this over, but see if you can kind of see this kind of like a string. I just want to see how fast the wave energy is going, or the wave itself, the pulse, goes back and forth. So right now there's not that much tension in it, and I can make a little disturbance, and it travels back and forth, right? I can make it less tension, it kind of ripples, but you can kind of see it bounce back and forth. But then I can make quite a bit more tension, and hopefully you can see there that it travels much faster when there's more tension in it. Much faster. And if I pull it too tight, the whole thing will fall over, but bounce it back and forth really fast. Whereas when there's hardly any tension, it doesn't go relatively that fast. As you get it tighter and tighter, it goes faster and faster. So that's really just showing the variance with respect to the tension. I'm varying the linear mass density a little too as I stretch it more and more. I have a smaller linear mass density, so that affects the velocity, also increasing it. But this is what we get. It's a nice first order expression, but it's a good expression at that. Very good for approximations on how fast transverse waves travel across the string. So the main thing to be careful of is this T here. T is tension in what? Newtons, that's right. Don't confuse this with the period of the oscillations. There's two capital T's when we start dealing with waves on a string. One's the period, and one is the tension in the string itself. And this again, linear mass density, mass per unit length, that just depends on the composition of the string itself. We'd be keeping both constant. Or we could vary this and see how the velocity varies. But anyways, that's what we've got for waves on the string. What I'd like to do at this point is do a couple little problems involving waves on a string and kind of deal with the basics, as well as kind of take a nice look at the phase constant. So a little bit different how we approach the phase constant with the waves, traveling waves, than with respect to the simple harmonic oscillator. Going to be a little bit more careful with waves in general. All right, so I'll be right back, and then we'll go ahead and do a couple problems here. Give me a sec. All right, so let us go ahead and do a nice problem, a couple problems. Let's just start out. Here's the first problem. All right, so we've got ourselves a wave that is modeled by the expression y of x and t is equal to 0.12 meters times the sine of say 16x minus 70t. And we're assuming SI units for all this stuff. Putting the units here gets a little bit messy, in my opinion. Anyways, there's our expression regarding this transverse wave on a string. And we want to know some things like, hey, what is the wavelength, the wave speed, the amplitude of the wave, the angular frequency, the linear frequency, the period, which way is the wave traveling, what's the phase constant, just all the particulars. And all that stuff's extractable from this expression. You have the expression, you have the ability to say, oh, this is the amplitude, this is the wave speed, this is the wavelength, and so on. So we kind of go down the road here. What is the amplitude? The amplitude is A, and that is 0.12 meters. Plain and simple. How do we know that? Because we do a direct comparison to the function that describes y of x and t is equal to a times the sine of kx minus omega t plus feet. This is minus plus general expression, but there we go. So we get A. What else do we want? Well, we want to know what is the wavelength. What's the wavelength of the wave? The wavelength is a lambda, and a lambda is equal to 2 pi divided by k, which in this case is going to be 2 pi divided by 16 radians per meter here for the wave number k, and we can go ahead and compute that out to be 2 pi divided by 16 gives us a wavelength of about 0.3927. 0.3927 meters. 39.3 centimeters, whatever, but we've got it. There's the wavelength. Well, what else do we want? How about we figure out what the period is, the period of the wave period. T, capital T here. I'm going to write period because we don't want to get confused with tension. Anyways, we've got the wave period. What's that going to be? Well, that is equal to 2 pi divided by omega. And what is omega? Well, omega is this term right there with the t, which is 70. So we've got ourselves, the period is 2 pi divided by 70. That is radians per second. Radians cancel out. We get a time in seconds. And we've got ourselves 2 pi divided by 70 gives us 0.08 0.08976 seconds. 976, yes. Round it off like that. So there we go. Pretty small period. 8/100ths, 9/100ths of a second, really. Almost a tenth of a second. But there we go. There's the period. The time it takes for one full cycle to be completed. What else? What else were we asked? What's the phase constant? The phase constant is equal to, there is no other term there, so the phase constant has to be equal to 0. Ooh, that's nice. And which way is this wave traveling? Well, because it is minus omega t there, this is plus, we don't have to rearrange anything, and we are left then with, it is traveling to the right, or really in the positive x direction. Plus x, generally just say to the right. And oops, I left that one out, but that's okay. It goes with the direction, that is, what is the wave speed itself? The wave speed itself is equal to the wavelength divided by the period, or equivalently, the omega divided by k. Let's do omega over k, which is going to be equal to 70 divided by 16. Again, omega is radians per second, and then k is radians per meter, such that we'll get meters per second here, which is good. We got 70 divided by 16 gives us 4.375. 4.375 meters per second. So the wave traveling at this rate to the right has a period of just about 0.09 seconds and a wavelength of really close to 40 centimeters. Amplitude 12 centimeters. And there we go. Some pretty simple things to ask about it. So then we go on. So this was a part A. We go on and say, well, what about part B? Part B says, what is the transverse velocity of the wave at the position 1 meter at a time of 3 seconds? So how are we going to get that? Well, we got a function that describes the transverse velocity of a wave traveling to the right, and that is negative a omega times the cosine of kx minus omega t. Phi is equal to 0 here, so just leave it out. So we've got this. We know what a omega is. We know what k and omega are. We already said omega. We'll just evaluate this at 1, 3. So we'll go ahead and do this. V sub y of 1 meter at 3 seconds is going to be equal to negative 0.12 meters times omega, which was 70 radians per second multiplied by the cosine of 16 times 1 meter minus 70 times 3 seconds. So again, this has radians per meter, such that radians per meter times meter just gives us radians. This is radians per second, such that radians per second times seconds gives us radians. Thus, this argument here is in radians. What does that mean for our calculator? Calculator better be in radians if you're evaluating this. So that's exactly what we're doing. Let me go ahead and switch over to radians because I was in degrees. And we can go ahead and do this. Negative 0.12 times the cosine of 16 minus 70 times the 3. And get ourselves a transverse velocity of negative 0.1068. It's negative 0.1068, and that will be meters per second. So there we go. There is the transverse velocity of the point 1 meter over from x equals 0 at a time of 3 seconds. That's what it's doing. It's going downward because it's negative, and that's how fast it's moving downward at that point. Well, we can also ask, what is the max? Vy max. Well, that's just equal to the amplitude of this function here, which is going to be equal to just a omega, plus or minus, really. Plus or minus. So we could compute that. So we've got the maximum value is 0.12 meters multiplied by 70 radians per second, which 70, 1484. That's okay. 0.12 times 70, 8.4. 8.4. 8.4. 0.12, yeah. 8.40 meters per second, plus or minus. So this is going relatively slow compared to what its maximum rate is. Can we make any conclusions regarding where it might be position-wise? The answer is, yeah, we should be, because when we're really close to the equilibrium position, it should be going pretty fast. This is as it goes through the equilibrium position. If it's going really slow compared to that, we should figure that we're probably getting pretty close to the endpoints, which are plus or minus a. This is almost 0 compared to this, right? So we should be very near one of the endpoints, either plus or minus a. Could we figure that out? Yeah, of course we could, and we'll come back to that. But let's get what the transverse acceleration is at that point. A sub y at 1 meter 3 seconds is going to be equal to, well, the transverse acceleration is negative a omega squared times the sine of kx minus omega t. So if we go ahead and evaluate this, we've got ourselves a sub y, and this was just in general. That is just a sub y. Now we got a sub y of 1 meter 3 seconds is equal to negative a times 70 radians per second quantity squared times the sine of 16 times 1 meter minus 70 times 3 seconds. Again, evaluate this out. This is 0.12. I don't know why I put a again, but 0.12, it's not 1.5, 0.12 times 70 squared times the sine of 16 minus 210 is negative 413.0 meters per second squared. I saw something on here. Sure got that negative sign there, good. And this, somehow I put in 0.15 here. Sorry, this value is off a little bit. Not too bad, but catch it, did not catch it. So this should be negative 0.08542 meters per second. A little bit less. I accidentally put 0.15 there for the amplitude. That's all right. That's all right now. This is good as well. There we go. A couple things there. Fantastic. So what do we have? We've got an acceleration that is negative, and we've got a velocity that's negative in terms of the transverse sense of this. So could we figure out approximately where it is? Well, let's just look at the max value first. A sub y max is going to be plus or minus a omega squared, which is 0.12 meters multiplied by 70 radians per second quantity squared, which gives us 0.12 times 70 squared gives us, 0.2 times 70 squared. 588. 588 meters per second squared, and that is plus or minus. So that is the maximum acceleration that this object, that this element can have, that really any element can have. And here is the acceleration at the position x equals 1 meter at the time of t equals 3 seconds. Negative. So what does negative mean? Well, negative means that the acceleration is pointing downward in the same direction that the velocity is pointing. So we have that the velocity and the acceleration both have the same sign. What does that tell us about the transverse velocity? It's increasing right now with respect to time. It should be increasing. Yeah. So this object is traveling downward and increasing its speed. Can we make some sort of conclusion about where it has to be? And the answer is yeah, definitely. Because we know that it's moving downward, that's great. And we know that it is not moving that fast compared to its maximum value. So it has to be fairly near an endpoint, give or take some amount, but near plus or minus a. Then it's a matter of, well, which one it's near. Is it above equilibrium or below equilibrium? Is it near a or near negative a? And the answer is found by looking at the sign of the acceleration, because the acceleration is always back towards the equilibrium position. So here's equilibrium, here's an element, it's accelerating downward, and then as it goes through equilibrium, the acceleration changes to upward. So if it is above equilibrium, the acceleration has to be negative. If it's below equilibrium, the acceleration has to be positive. So this brings us to the conclusion that this element at x equals 1 at t equals 3 seconds has to be above the equilibrium position near y is equal to a, and it has to be traveling downward. So if we were to go something like this and just kind of draw out the wave and say, oh, where's x equals 1 at t equals 3 seconds? What does it kind of look like? I'm not really worried about how far over we are. We'd have to be some number of wavelengths over, but it's more about being able to discern where you are in a cycle, right? So where should we be? Well, the object needs to be traveling, excuse me, I keep saying object. The mass element at x equals 1 meter has to be traveling downward. So, and it has to be near x equals positive a. So if we say here's x equals positive a right here, what side of it is it on? Well, if it's on this side, we look at what's coming next. This peak here is coming next. So as this wave moves this way, this element would be moving up. That would be positive velocity. So we look over here. This wave part right here would be moving down in the same direction as the acceleration. So we would go ahead and say, well, it's got to be somewhere like here. This is x equals 1 at t equals 3. And again, this is approximately, but this is what we'd have. This element would be traveling downward, v sub y, and would also have a pretty big acceleration, a sub y, because again, it's fairly near its maximum value, which is at x equals a. So could we make sure? And the answer is, of course we could. Of course we could. So how? Well, we go ahead and look at the function, right? Y of x and t is equal to a times the sine of kx minus omega t. We just evaluated it. y is equal to 1 meter at 3 seconds is equal to 0.12 meters times the sine of 16 times 1 minus 70 times of 3, which gives us y of 1, 3 is equal to, should it turn out to be positive or negative? Better turn out to be positive, right? And it better be pretty close, pretty far away from the equilibrium position. We should say that. Pretty far away from x equals 0. So let us look. 0.12 times the sine of 16 minus 210 gives us positive 0.0843, we'll just call it 0.0843 meters. 8.43 centimeters. The maximum here is 12 centimeters, or 0.12. So could this be 0.083? Sure. Sure, that stands to reason. That element's going down, the acceleration's down. There we go. There's where it would be within the cycle that that element is constrained within. Pretty cool, yeah? Heck yeah, it is. So, there we go. There we go. Last question. Now is kind of checking some stuff out. We have that the linear mass density, so this would be like a part A, B, C. This should have been C. This will be a D. We're given that the linear mass density is equal to 45 grams per meter, mass per unit length. And we want to know, what is the tension in the string? Equilibrium tension. So how are we going to get that? Well, we note that the wave speed is equal to the square root of the tension divided by the linear mass density. So we could just go ahead and solve this for the tension, and we've got that this goes to, we'll square both sides, multiply both sides by mu, and we've got the tension is equal to mu times d squared. Which v are we talking about here? This is the wave speed. Wave speed. This is the tension, this is the linear mass density. So when we go ahead and compute this, we want to have mu in, not grams per meter, we want it in kilograms per meter because we want SI units. So how are we going to convert that? Move the decimal place to the left 3 times, and we've got ourselves 0.045 kilograms per meter multiplied by the wave speed of 4.375 meters per second, quantity squared. And we've got pretty small tension here, that's okay. 0.045 times 4.375 squared. We've got a tension of about 0.861 newtons, we'll just call it. 0.861 newtons. Equilibrium tension in the string. Great. So there is one problem. Good. Did we do anything with the phase constant? No. So that's coming next. So let us go ahead and give me a chance to erase this all. We'll look at that, and then we'll move onward. All right, be right back. All right, so let us do another problem with waves on a string. This time we're looking at the phase constant and some other aspects of it. But yeah, here's the problem. All right, so we've got ourselves an oscillator that is in contact with the string. We'll say a string's connected to the oscillator, and the oscillator has a frequency of 25 hertz. Thus, the string oscillates up and down at any given position with the same frequency as the oscillator. That's what's driving the string to have its transverse oscillations. And we measure out the wavelength of the waves on the string, and we say that, oh, we find that lambda is equal to 30 centimeters. And we also measure the amplitude of these waves to be 0.15 meters. All right, so we've got 15 centimeter amplitude waves. So that's a pretty good size amplitude. 30 centimeters long, and yeah, the frequency 25 hertz. And what does it want? Write the expression. The expression for this wave. Well, what do we have for the expression? We know that y of x and t is equal to a times the sine of kx minus omega t plus phi. Now, we're not given any information in terms of a phase constant, but we do have the ability to find a, k, and omega. A is already given. What about k and omega? Well, k is equal to 2 pi divided by a lambda. That's the wave number there. So we can go ahead and compute the wave number. We've got 2 pi divided by 30 centimeters. We want k in radians per meter. So we'll change that to 0.3. We'll write this 2 pi divided by 0.3 meters is equal to 20.944. Call it 20.944 radians per meter. So we've got ourselves k. Then what about omega? Well, this is not omega. This is the frequency in hertz. We want omega, the frequency in radians per second. So how are they related? Well, omega is equal to 2 pi times f. That's it. F is equal to omega over 2 pi, or f is the inverse of the period. But there we go. So we go ahead and compute this. We've got 2 pi times 25 hertz, which will give us radians per second. So we've got 50 pi, which is about 157.08. 157.08 radians per second. So we don't know what phi is. That's okay, but we can still write the expression now. We've got that y of x and t, displacement as a function of position and time, is equal to 0.15 meters multiplied by the sine of k, which is 20.944, times x, minus omega, which is 157.08 times t. And then we can add in a plus phi, and we were told that this is traveling to the right. And thus we used minus here, and I wrote minus there. It said traveling to the right. All right, so there we go. Fantastic. Well, from this we could discern all sorts of things like we did in the last problem, right? Once you have this function, we could figure out what the wave speed is, we could figure out what the transverse velocity at some point, at some given time is, up to this phase constant, and things like that. So let us work on this phase constant a little bit and try to make some use of it. So now we'll say part B. If the string element at position x equals 0 at the time t equals 0 is at positive, what do we have, 8.15? Let's say 0.11 meters. That element x equals 0, t equals 0, 0.11 meters, and is moving downward. What is phi? That's what was asked. Just kind of restatement there so I can look at it and say, okay, well, we've got some initial state of the system, right? X equals 0, t equals 0. We've got a particular displacement of that element at that time, and we're also told what direction it's moving in at that element's position at that moment in time. So we go ahead and we say, well, what do we know about this stuff? Yeah, we know the function. We know that y of x and t is equal to a times the sine of kx minus omega t plus phi. Well, we know a, k, and omega, great. And then we can evaluate it at 0. y of 0, 0 is equal to a times the sine of, well, that's 0 and that's 0, which just leaves us with phi. Well, what does this have to be equal to? It has to be equal to positive 0.11. 0.11 meters. That's what we need. So we just go ahead and figure this out then, right? We'll solve this out for phi. And we've got ourselves, well, the sine of phi is going to be equal to 0.11 divided by a, which is 0.15. And thus, from this, we can get, I'll do it in a step here, 0.11 divided by 0.15. Great. We solve this out for phi. Phi is equal to arc sine of 0.11 divided by 0.15. And make sure that, again, that we're in radians here. We want phi in radians. And we've got the arc sine of 0.11 divided by 0.15. Great. And that says 0.8232. 0.8232 radians approximately. There we go. Is that really the phase constant? And well, that's where that second piece of information comes in. It's moving downward. For this to be the right phase constant, it has to have a negative velocity. So we have to check. Check v sub y and see if we get the correct sign. Moving downward equals negative, right? So let us go ahead and look at this. V sub y of 0, 0 is equal to negative a omega times the cosine of kx minus omega t plus v, but x and t are 0. So this just leaves us with this, again, evaluating the transverse velocity at t equals 0. So if this is going to be equal to a negative, which it must be if it's traveling downward, then the cosine of phi must be equal to a positive, because a and omega are both positive values. So we must have that the cosine of phi is equal to plus. So then check. The cosine of phi, well, we said that phi is 0.8232. 0.8232 is equal to, cosine of that gives us plus, 0.6799. Plus 0.6799. Check. So for this initial condition, phi is indeed equal to 0.8232. 0.8232 radians. That seems pretty easy, right? That's kind of the same thing that we did with the simple harmonic oscillator. And the answer is, yeah, that is the same thing. Fantastic. Well, let us do this then. And see if it's really completely the same. If there's some subtle difference that we have to be wary of. And hopefully the latter you're probably suspicious of now. All right, so what if it were traveling upward? Instead, this is regarding part C. Excuse me, part B. So instead of traveling downward, we say, hey, it's traveling upward. What's the phase constant then? Well, it can't be that phase constant, because that phase constant gives us that it's traveling downward, right? We just checked it. That's it. So now we've got this to go with. We've got that v sub y has to be equal to positive because it's traveling upward. And this is v sub y of 0, 0. I should put that in. V sub y of 0, 0 must equal to a positive, and thus the cosine of phi must be equal then to a negative. Again, by the same logic that we had right there, negative a omega cosine phi is giving us the sine correlation. Now it has to be positive, so the cosine of phi has to be equal to a negative value. So it's negative times negative gives us a positive, positively. Well, that gives us a positive cosine of that phi. So what's the other phi? And maybe you say, oh, well, it's got to be the negative of this, just like with the simple harmonic oscillator. Say, oh, yeah? Okay, let's check this out. Let's try that. Let's do the cosine of negative 0.8232. Oh, shoot, I get the same exact answer, positive 0.6799. If I stick in negative here, I get the same result, which still says that it's traveling down. Oh, shoot, that's not good, right? How do I get the cosine of phi to be negative? Whew. Well, got to remember, cosine is what kind of function? That's right, it's an even function. Plus or minus gives you the same output. So we can't use plus or minus. Why could we use it with the simple harmonic oscillator? Because for the simple harmonic oscillator, we had sine. The sine of phi was correlating with the direction of the oscillation, up or down. But for the waves, it's the cosine of phi that's correlating with it going up or down. So what are we going to do? Oh no, what are we going to do? Well, it can't be plus or minus. That's the bottom line here. We have to look back at the position-wise. There has to be two positions that give us the same speed, but one gives us a positive up and one gives us a negative down. We've already got the negative, so what's the other position? What's the other, really, I shouldn't say position, I should say, what's the other phase constant? So here's a little thing that we've got going on. So we can say x is equal to 0 anywhere. X equals 0, t equals 0. Let's just say that it is somewhere around in here. X equals 0, t equals 0. Well, if I look at this point right here, hey, that's the point that is a little bit below the amplitude. We'll say that that is y is equal to 0.11 meters. There it is. As this wave moves that way, that would be going downward. So that matches part B, right? And it's good. So the phase constant, if x equals 0, t equals 0 is that spot in the wave cycle, then there is the phase constant. But there's this other position right here. This position right here has the same y value, the same displacement, but we look at what's coming in behind it. This position is going upward. V sub y is equal to positive. This is the one that we want. And this again is the sine function describing how this wave is spatially laid out in space and time. So what do we have to look at? Well, we have to look at symmetry. Symmetry. There's two phase constants that give us these two different positions here, or correlate with the specific initial state of the system. So we want this one now to be x equals 0 at t equals 0. That's how we want to start it off. So what's the phase constant for that? Well, what can we do with this? Can't look at cosine really. We can look at sine though. There are two different phase constants that'll give us the same position, but give us different signs for cosine. And what we can do is sort of look at, again, symmetry there. Cosine is symmetric about the x-axis, just the cosine function. Sine function is symmetric about the y-axis. So if we start thinking about like vectors in a sense, not that this is really vectors, it's a way that I like to associate it. If I take just some vector here like this, and say we got some vector, well if it's projection onto the x-axis, would give us the same thing that we had, whether it was plus, let me not use a, plus theta or minus theta, right? And we know that cosine goes with the x-axis in terms of figuring out the projection. But what about the y-axis? Well, y-axis, I can have this here, the projection of this and the projection of that would give us the same amount, and this goes with the sine of, well, what I'd want to call phi. So I could call this phi, not call it phi, this total angle phi there. So that the sine of phi is equal to the sine of theta. So it gives us the same displacement, but the cosine of phi versus the cosine of theta would give us an opposite sign for cosine, as with respect to theta. So this is what we get out of it. Whether that's truly helpful or not, it's hard to say, but anyways, we want this angle here. Our other phi, if this is one of the phi's, our other phi is this angle here. So how do we get that? Well, we could take and note that this is also the same as plus theta right there because of symmetry. And then we can take 180 minus that. So we could call this phi1. And then there is actually a phi2 that is 180. Let me not say 180. Let me say pi radians. Just pi minus phi1. There's two answers ultimately that will give us the same position, the same displacement. But one gives us a positive, and one gives us a negative regarding the velocity. So let's try this out. Phi2 is equal to, that's equivalent to 180 degrees minus that phi1. So we've got ourselves pi minus 0.8232. 0.8232 gives us 2.318, we'll call it 2.318 radians. Now let us check out the cosine of this. Cosine of 2.318 radians, well, again, we need it to be equal to a minus if the object is to be moving downward, and that follows from that right there. So what is the cosine of this? Cosine of that gives us minus negative 0.6799. Well, that's the same thing. Same quantity, but negative. Positive, negative. But both of the sine of this and this correlate with the same position. That's great. But ultimately, this is the one that gives us V is upward, V sub y is upward. Thus, for this part C, phi has to be equal to 2.318 radians. So that V sub y of 0, 0 is equal to positive value, so that it's going up. So a little more subtle than with the simple harmonic oscillator where it was just plus or minus. Now it's whatever that arc sine gives us, and then it is that or pi minus that for theta 1, theta 2. Then you can check them both, see which one gives you the right correlation with the directionality, transverse-wise. Whew, fantastic. All right, so that's it for right now. Phase constants are good stuff. And until next, be well.